Hey everybody, welcome to chapter 13. We're going to talk about a new kind of t-test that a lot of people call a paired samples t-test, but you'll also hear it be called a related samples t-test or a dependent samples t-test. And basically what this is saying is that we're going to have one group of participants and we're going to measure all of them on a particular variable 2 times. Okay, so it's all the same people, but they've given us 2 different measurements. That's why it's related or paired or dependent data, and therefore we're going to run a paired samples t-test. So let's jump into that. First up, a quick review question. If you want to compare a sample mean to a population mean, and you don't know the population standard deviation, which test do you need to use? The answer here is B, a one-sample t-test. If you don't know the population standard deviation, you got to use a one-sample t-test. If you do know the population standard deviation, you can use a z-test. So first up, let's talk about research designs that involve related or paired or dependent data from your sample. There's a lot going on this slide, but let's start with the bottom of this diagram with the within subjects design. So the bottom left of this is showing a circle with basically your sample in it, right? Your study sample. And what this is showing with the arrows is that you take everybody in that sample and you put them in some kind of condition. This says treatment 1. That might be like, okay, if the goal of this is to try to treat people's anxiety, maybe treatment 1 is a drug. And then you go through and get an average anxiety score after that condition is met. Then you go to the next condition, treatment 2, which let's say is talk therapy. Okay, then you measure all of the samples, the participants' anxiety scores after that, and then you go put them into another treatment, which is maybe cognitive behavioral therapy, and you again after that get an overall average anxiety score for all your participants. So all of your participants are undergoing all of the different treatment conditions, right? Versus a between subjects design, you've got a pool of people, your sample, and you split up that sample into different groups of people. And so treatment 1, who is experiencing the drug to lower anxiety, that's one group of people. That's a subset of your sample. Treatment 2, which would be the talk therapy, that's a separate group of people. Treatment 3 was cognitive behavioral therapy. Again, another separate group of people that you've pulled from your sample, and then you compare each of the average anxieties between those groups versus the within subjects design. You're comparing the average anxiety from different conditions, but it's in the same people. Now, this would be a little sneak peek because if you have more than 2 groups, more than 2 conditions, more than 2 groups, more than 2 treatments, more than 2 whatever that you're going to be comparing the average scores of, then you're going to need to use ANOVA, which we'll talk about in future weeks. But if you only have 2 treatment groups and you're comparing between subjects designs, then you're going to be using an independent samples t-test, which we'll talk about next chapter. But if you're comparing 2 groups and you subject all of your participants to both of those situations, then you're going to be using what we're doing today, which is a dependent samples t-test. So in our within subjects design, all the data for a specific variable are collected on the entire sample in multiple different environments or conditions. And a really common design that we use all the time is called a pre-test, post-test design, where you gather the data, you collect data on your sample before you actually submit them to any kind of experimental manipulation or condition, or give them a drug, or have them go through a program or something like that. And then after you put them in that condition, you then measure that same variable on the same people afterwards. And so then you can compare the same variable from before to after whatever the treatment was. So the terminology here is we're using, again, the same participants are participating in two different kinds of situations or conditions. And so what happens is each person, each participant, will have a pair of scores, the pre-test score and then the post-test score. And those are a pair of scores that are dependent on one another. They're not completely independent, because knowing something about a participant's pre-test score should give you kind of an idea about, well, what-ish should their post-test score also look like. So this is going to be pretty similar to the one sample t-test that we did in the last chapter, except in the one sample t-test, you are having individual scores for your subjects or your participants in your sample, and then you find the average of those, and you compare that average to some comparison population and see if the average of your sample was significantly higher or lower or not than the population that you're comparing it to. But instead of having individual single scores, well, now we've got pairs of scores. And so what do? Because we still want to get that down to a single score that we can get an average of and compare it on some kind of distribution. So we actually just take the scores from the pre-test and the post-test, and we find the difference of those. So then we can use one score, get an average of those, and put it on a comparison distribution of means. So in order to calculate these different scores, which are represented by an uppercase D, all we got to do is subtract one of the scores from one condition from the score from the other condition. But you do want to be careful about this, because whichever score you subtract from whichever other score, and you can do it in either way, but the interpretation of the results will change based on the order that you do this in. And so let's give an example of, like, if you wanted to try to increase people's self-esteem, you take a measure of their self-esteem. This is the kind of pre-test, and then you have them remember something that makes them feel really good about themselves, and then you measure their self-esteem right after they have this memory, right? So probably for a lot of people, their self-esteem went up after they remembered something good about themselves. Well, if you took the post memory, this is the post-test self-esteem score represented by X, that subscript post memory, and you subtract it from X pre-memory self-esteem, you'd probably get a positive number, because you know on average people will have higher self-esteem afterwards, and you subtract a smaller number from that, you get a positive thing. And so it would be the opposite, right? If we did the pre-memory score, subtract the post-memory score from that, you'd get a negative number. And either way is fine, but you just have to know what those things mean when you're actually interpreting the difference and whether something's increasing or decreasing from pre-test to post-test. Okay. So the first thing that we do is we calculate a difference score on this variable for every single participant in the study. And then we're going to actually calculate the mean of those different scores, which is represented by D bar, by adding up all those different scores and then just dividing it by the total number of subjects, because that's the total number of pairs of scores that you have. And then we can use this mean of the difference scores to actually calculate a t-statistic and compare that to a distribution of means. So for example, if we wanted to calculate the difference scores for a parent who describes the amount of sleep that they get before they have kids and then after they have kids, right? So for instance, you can see that before they have kids, they have 10 hours of sleep per night. Very nice. After they have kids, they only get 4 hours of sleep per night. If you take the kind of post-test, which would be hours of sleep after kids, and subtract from it hours of sleep before kids, 4 minus 10 gives you a difference score of -6. And that's probably how you would want to look at it, because -6 is telling you that their sleep is going down from before kids to after kids. And that makes a lot of sense. So that's probably how you would set it up. And kind of traditionally, we do take the post score minus the pre score. So in this case, we get a difference score of -6. Now we're going to do that for every single participant in our study, right? And so let's just imagine we have 2 participants now. Hours before sleep, or rather hours of sleep before kids, are 10 hours for the first participant, 8 hours for the second participant. And after they have kids, the first participant gets 4 hours of sleep, like we saw. And now the second participant gets 6 hours of sleep. Okay, so we calculate different scores for each of those participants. They have -6 and -2 respectively. But now we want to calculate the mean difference score. Okay, so the mean of the difference scores. And that gets us to a point of which we can finally go on to calculate a t-statistic, a t-score. So we're going to get the average difference score from all of our participants by taking every difference score, adding it together, and dividing by the number of people in the sample. And that mean of the differences, again, is called d bar. So let's walk through an actual example of how to calculate a paired samples t-test using an example you will remember from last chapter. All right, so let's use an example. It's going to be kind of a weird one, but a fun one, hopefully. So what if we wanted to know whether people who are self-described psychics are able to correctly predict the suit of a card from a 52 card playing deck, whether they're more accurate in those predictions when they're in a lab room, when we actually take them into a lab room in a psychology building or something like that, versus the same people trying to predict the suit of cards in a fortune-telling room, because maybe they'll be more comfortable, they're kind of in their natural element, right? So maybe they'll do better at predicting the suit of cards in a fortune-telling room as opposed to in some kind of lab room. So let's say we get a sample of 50 psychics. Let's set up our hypotheses. So as always, step 1 in the hypothesis testing procedure is to state our hypotheses, or hypothesis in this case. Our alternative hypothesis is going to be that we expect the psychics to have a higher accuracy for predicting card suits in the fortune-telling room compared to the lab room. So higher accuracy in the fortune-telling rooms because, this is their home territory, this is where they're most comfortable, maybe they're just better in that situation. The null hypothesis, of course, is the opposite of that, so they will have equal to or worse accuracy in the fortune-telling room compared to the lab room. And we want to pay attention again to the order in which we do the subtraction of the difference scores. If our alternative hypothesis is that we're thinking they'll have higher accuracy in the fortune-telling room, we probably want to start with that number first, because then if you subtract the accuracy in the lab room, you're expecting positive difference scores, which will indicate that yes, indeed, they do better in the fortune-telling condition. Whereas a negative score would indicate that overall, the psychics actually do better in the lab condition, right? Because if their ratings of accuracy are higher in the lab condition on average, then when you subtract the lab from the fortune-telling condition, you'd actually get negative numbers. So that's one way to talk about the alternative and null hypotheses. Here's the other way, maybe kind of more of the scientific way to talk about it. In the psychic population, the mean difference score between conditions should be greater than 0. So what would that mean? Well, because we think that the psychics will have a better accuracy in the fortune-telling condition as opposed to the lab condition, then once you, for each participant, make all of those subtractions and you find an average difference score of the entire sample, that number, whatever that average difference score is, should be greater than 0, right? Because on average, you have higher numbers in the fortune telling condition than in the lab condition. So on average, you get a number that's greater than 0. So now our null hypothesis is going to say that we are going to have no significant differences between those conditions in terms of accuracy. Well, if there's no significant differences, then the numbers should cancel each other out, right? Because like the accuracy in the fortune telling condition shouldn't be any different from the accuracy in the lab condition. And so an accuracy of 25 in one condition and 25 in the other condition, subtract those, what do you get? You get 0, right? So ultimately, we're actually comparing the average difference score against a hypothetical average difference score of 0. So that's what's going to be on our t distribution of sample means. We're not comparing it to an actual population. We're comparing the mean difference score that we get from our sample to basically this like fake theoretical t distribution of let's see, t distribution of mean difference scores. That's going to be a lot later on. And we assume that the mean of this t distribution of mean difference scores to be 0. So we're going to see whether our sample mean difference score is less than that, more than that, or equal to 0. And step 2, we always set our decision criterion, which of course, again, is always going to be alpha level of 0.05, which we'll compare our p-value to eventually. We also need to know our degrees of freedom in order to look up the t critical value, which is going to, and we do that in a t table, which is going to set up the critical regions. And if you were going to use a alpha level of 0.05, this is a one-tailed hypothesis because it's a directional hypothesis. We think that psychics will actually do better in one of the rooms. Degrees of freedom are going to be 49 because 50 minus 1 is 49. If you look that up in a table, again, you get this t-crit value of 1.677, which means if we calculate a t-statistic equal to or greater than that, it'll fall in the rejection region or the critical region, and we can reject the null hypothesis. In step 3, we're going to actually recruit these 50 psychics and have all 50 psychics do all of the card guessing trials in both of the rooms. So they have to do 100 trials in the lab room and 100 trials in their fortune telling room. If this was a between subjects design, which it is not, you'd actually have to get twice as many participants. You'd have to get 100 psychics and randomly distribute 50 of those psychics into each of the conditions. And so you'd have 50 psychics do the guessing in a laboratory condition, and you'd compare that average to the other 50 psychics, completely different group of 50 people, who do this prediction challenge in the fortune telling room. In step 4, we have to calculate our statistics, and in order to know which statistical test we actually need to conduct, we can use this again, same handy-dandy flowchart. We're comparing means. How many sample means? Well, now we actually have 2. And is it a between subjects or within subjects design? It's a within subjects design, which means we need to use a paired samples t-test. So first things first, we are going to calculate the estimated standard error, which is similarly done to the last chapter with a one samples t-test. Now this is a dependent samples or paired samples t-test. We're going to use the estimated standard error of difference scores. And so that's going to be the standard deviation of difference scores, SD, divided by the square root of our sample size. And let's say that we find out from our data that the standard deviation of difference scores is 2.9. We know that we have 50 people in the sample, so 2.9 divided by the square root of 50 is 0.41. And we're going to plug that 0.41 then into the denominator of the new calculation that we've seen the variation of this in the one sample t-test, but it's a little different now that we're talking about paired sample t-test. We have to know, first of all, d bar, which is the mean difference score for the sample, and let's say it's going to be 1. And then we're going to subtract from that the population mean difference score, mu subscript d, which, as we know from our null hypothesis, this is the comparison that we're trying to compare our sample's mean difference score to. We're going to use a population mean difference score of 0, which would indicate no difference between pre-test and post-test. And we take 1 minus 0 and divide that by what we just did with our estimated standard error. And so we get 1 divided by 0.41, which is 2.44. That's our t-value or t-score for our paired samples t-test. And I just want to really quickly rerun through some of those equations. So we've got the estimated standard error. We've got the calculated t-value that uses the estimated standard error in its denominator, right? But if we kind of fully plug in that estimated standard error into that denominator, we get the full equation on the bottom here. And that should look similar to what we've been doing before in terms of z-test and one sample t-test. Basically, it's just that in this case, the t-score equals the mean difference score, d bar, minus 0, which is the population mean, divided by the standard deviation of difference scores over the square root of your sample size. So now we can set up our t-distribution of means of difference scores. That is a mouthful. In the one sample t-distribution or one sample t-test, we were talking about a t-distribution of means, a distribution of means like we've been talking about kind of this whole semester. Well, this is not a distribution of means of a lot of samples. It's the distribution of mean difference scores of a lot of different samples. So it's another step, kind of a little bit more difficult, but the same rules apply. So we first used a t-table to look up the t-critical value of a sample of a size 50, which means degrees of freedom of 49. We're using a one-tailed t-test, one-tailed hypothesis test with a p-value or alpha level of 0.05. That establishes this 1.677 t-critical value, and anything more extreme than that is going to be in the critical region. Well, we just calculated a paired t-test value or t-score of 2.44. And where does that fall in this distribution? Definitely to the right of that critical value, which means it belongs in the critical region. And since that's the case, we can reject the null hypothesis and conclude that the alternative hypothesis is true. So ultimately, what can we say? Well, we know if the alternative hypothesis is true, then a lot of these other things all are true at the same time because the alternative hypothesis is true. First of all, there is an effect of condition on card prediction accuracy. If there was no effect, then the mean difference would be not significantly different from 0. But there is an effect of condition because the accuracy was higher in the fortune-telling condition than it was in the lab condition. Number 2, the mean difference score for the sample is significantly different from 0. If it was not significantly different from 0, then our t-value would not have been this extreme, and it would not have been in the critical region. It would have been closer to like the middle of the distribution. And number 3, we can say that the mean prediction accuracy is statistically significantly higher in the fortune-telling room compared to the lab room. So we rejected the null hypothesis, we accept the alternative hypothesis, and what happens now? Well, this single study provides some evidence that the room that a psychic is in actually affects their accuracy rates. However, one, we could still be making a type 1 error, like statistically speaking, this could all just be not true, and we could have decided that there was a statistical significant difference when in fact there was not. And also, in addition to that, this study does not answer the question of whether psychics can predict better than chance. You see, that's not what this test is set up to do. The test is only set up to say, are psychics better at guessing the suits of cards in one room compared to the other? It doesn't say whether that rate is better than guessing or the overall average population of people who are not psychic. So just as a bit of a recap, for a paired sample t-test, if the p-value of the null hypothesis is very low, and we didn't actually calculate this, but you'll do that during a lab for paired samples t-test. If it's less than 0.05, equal to or less than 0.05, you can conclude that the scores in each condition are significantly different from each other, and therefore the mean difference score is significantly different from 0. Now, in this lecture, we talked about a one-tailed alternative hypothesis. You could also make a two-tailed alternative hypothesis, which would just be that the scores in the two conditions differ. You just don't say in what direction. Therefore, the null hypothesis for a two-tailed test would be that the scores in the two conditions are the same. For example, a professor might use a paired sample t-test to understand whether there was a difference in student exam scores before and after completing a lab covering the content. But the key word here is there was a difference in exam scores, but they didn't say in what direction. So that would be a two-tailed hypothesis test. I couldn't find a meme that was specific to paired samples t-test, which is not that surprising, but I found this. It's a good substitute. I love this cartoon. It's called Strange Planet by Nathan Pyle, and I hope you enjoy this one as well. See you in the next lecture.